As you can remember, on our previous lesson, we obtained a differential equation of a small free oscillation without damping. This equation can be written in this way. Second derivative of coordinate, second derivative of coordinate by time, plus natural frequency to the power of 2, multiplied by coordinate x, and this is equal to 0. This is equal to 0. And today we are going to try to solve this equation to find the solution. Maybe you remember from calculus that the solution of this equation can be found as exponent of lambda t. It can be written x is equal to e to the power of lambda t. So let's try to find the solution in this way. To do this, it is necessary to find first and second derivatives. First derivative will be dx by dt is equal to lambda e lambda t. And what about second? What about second derivative? Second derivative is lambda squared e to the power of lambda t. Okay, so let's make substitution. Let's use obtained formula. Let's use this. We have that lambda to the power of 2 multiplied by e to the power of lambda t plus omega 0 to the power of 2 multiplied by e to the power of lambda t, and this is equal to 0. If we want this formula, x is equal to e to the power of lambda t. If you want this to be the solution, we have to find such lambda that will be a root of this algebraic equation. To do this, we can simplify this equation. We can write the equation for lambda. Lambda squared plus omega 0 squared, and this is equal to 0. This is equal to 0. This is equal to 0. This algebraic equation is also known as characteristic equation. This also known as characteristic equation. So let's solve this. Let's solve this. It will have a solution. Lambda is equal to plus or minus square root of minus omega 0 to the power of 2, and this is the same as plus or minus square root from minus 1 omega 0, or this is the same as plus or minus I omega 0, I omega 0, omega 0, where I is equal to square root of from minus 1. So here we have to use complex numbers. Not only real numbers, but also complex numbers. Because when we use only real numbers, square root of minus 1 does not exist in real numbers, but in complex numbers it does. In complex numbers we can write that some number is equal to, that number is equal to square root of negative value if we use complex numbers. Okay. So we have obtained that lambda may be equal to one of two values, plus I omega 0 or minus I omega 0. So we have two partial solutions, and solutions of linear homogeneous differential equation. And I hope that you can remember from calculus that if we have two partial solutions of linear differential equation, the linear combination of this partial solution will also be a solution of this differential equation. So general solution is C1 multiplied by e to the power of I omega 0 t plus C2 e to the power of minus I omega 0 t minus I omega 0 t. So a linear combination of partial solutions. What are C1 and C2? they are these are unknown integration constants. Integration constants. They may be found. They may be found. C1 and C2 may be found from initial conditions. Initial conditions. In this case, initial conditions are initial coordinate, and initial velocity. Initial means some value of coordinate or velocity at initial moment in time. Initial moment in time. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, if there is no questions, so we have obtained the solution of the differential equations of small free undamped oscillations. We have obtained this solution, but this solution is not useful. In this case. It is not useful to describe small oscillations because it is impossible to see from this formula any properties of oscillations. So it is necessary to transform this formula. It's necessary to change this in some way. So let's try to do this. First of all, it is necessary to remember. So-called Euler's formula. I'll remind this. Euler's formula. It is from calculus. According to this formula, e to the power of I phi is equal to cosine phi plus I sinus phi. This is Euler's formula. And this formula may be useful in our case. So let's use this. Let's use this here. To change our solution. To transform it into more useful form. C1 multiplied by cosine omega 0 t plus sinus omega 0 t, but multiplied by I plus C2 cosine minus minus omega 0 t plus I sinus minus omega 0 t omega 0 t and now it is necessary to remember some properties of cosine and sinus. Some properties. Cosine of minus x is equal to cosine x. And or maybe let's and the sinus of minus x is equal to minus sinus of x. Minus sinus of x. So let's use this here. Let's use this here in our situation. Let's use these properties of trigonometric functions. Let's use this here. C1 cosine omega 0 t plus I cosine, sorry, sinus omega 0 t plus C2 cosine omega 0 t omega 0 t minus I sinus omega 0 t omega 0 t and we can rewrite this. We can write this in another way. We can write this in another way. We can write this in this form: C1 plus C2 cosine omega 0 t omega 0 t plus I C1 minus C2 sinus omega 0 t. Okay, do you have any questions? Do you have any questions about this? About
No, teacher.
no, okay. Okay, so let's continue. Let's continue. Let's continue, and because this is a good way to good way to remind calculus, for example. So let's make some new signations. Let's sign this sign this as A, and this we will sign as B. This we will sign as B, and according to these signations, it will be equal A cosine omega 0 t plus B sinus omega 0 t sinus omega 0 t. Okay, to prove that it is possible, it is necessary to find the connection between C1, C2, and A and B. So it is necessary to write the system of equation C1 plus C2 is equal to A, and I C1 minus C2 is equal to B. From this, we can obtain, if we change second equation, we will obtain C1 plus C2 is equal to A, and C1 minus C2 is equal to B divided by I. Maybe we can change this one more time. B divided by I is equal to B, or is equal to I B I to the power of 2, and we can remember that I is the square root of -1, so this will result -1, so this is minus IB. This is minus IB. So we have obtained that C1 plus C2 is equal to A, and C1 minus C2 is equal to minus IB. This minus IB. And how to solve this system of equation? We can use Cramer's method, or we can make some simple transformation. For example, we can add these two equations, and we will obtain that 2C1 is equal to A minus IB is equal to A minus IB. A minus IB. minus IB. And but I have made one little mistake. It is better to write this as minus B. Okay, a little mistake, and I have just noticed it. So let's write minus B instead of plus. So here we have plus. Here we have plus, and here it is necessary to write minus. Okay, it is necessary to write minus. This will be better. This will be better for further actions. So C1 is equal to A plus IB divided by 2. Or we can do another thing. We can subtract second equation. We can subtract second equation from the first equation. So we can obtain that 2C2 is equal to A minus IB and this is equal to this result that C2 is equal to A minus IB divided by 2. Okay, do you have any questions about this? Do you have any questions? No questions. No questions. Okay, so I will clean some unnecessary information from the screen, and left some information that we need. So this solution can be changed in this way. And it is possible. We have the connection between C1 and C1, C2, and A, B. So we can change our solution. Using this formula. But this second form, A cosine omega 0 t minus B sinus omega 0 t, this form is much more useful than previous form. This form is much more useful. Why? Because it doesn't contain complex numbers. It contains only real numbers, and this is more useful. Because all physical values that can be measured in experiment are real values. Not complex. And this form of solution contains only real numbers, and this is advantage. Okay, but this solution can be changed can be changed one more time. It can be changed. It can be changed one more time. To do this, let's do this transformation. Let's do next transformation. Divide and multiplied by this square root. By this square root of squared a plus squared b. This will be a divided by square root of plus b to the power of 2 cosine omega 0 t minus b divided by square root a to the power of 2 plus b to the power of 2 to the power of 2, and let's I will carry this here. I'll write this here. So sinus omega 0 t. So what can we do now? We can make some sinations. We can sign this square root as x xv. We can sign this as xv, and we can sign this as cosine alpha, and this is cosine sinus alpha. Sinus alpha. Why can we do this? We can do this because we have the main property of trigonometric functions. This must be equal to unit. This must be equal to 1. So let's check. Let's check this. Let's check this equation. Let's check this equation in our sinations. A to the power of 2 plus b to the power of 2 plus b to the power of 2 divided by a to the power of 2 plus b. So this will be a plus b divided by a to the power of 2 plus b to the power of 2, and this is equal to 1. This equal to 1. So we have obtained the correct result. And it means that we can write that a divided by square root and b divided by square root we can cite them as cosine and sinus. Okay, so we have written that xv is equal to square root of a to the power of 2 plus b to the power of 2, and cosine alpha. Cosine alpha is equal to a divided by square root of a to the power of 2 plus b to the power of 2. Sinus alpha is equal to b divided by square root plus b to the power of 2 to the power of 2. And it is better to sometimes it is better to use tangent alpha that is equal to sinus divided by cosine and this will be b divided by a. This will be b divided by a and divided by a. Okay, do you have any questions about this? No, that's great. So let's clean the screen. And we can write that this is equal to xv multiplied by cosine alpha cosine omega 0 t minus sinus alpha sinus omega 0 t sinus omega 0 t sinus omega 0 t. And let's remember some properties of cosine. Let's remember that cosine of alpha plus beta this formula is well known from math, and this is equal to cosine alpha cosine beta minus sinus alpha sinus beta sinus alpha sinus beta sinus alpha and sinus beta sinus alpha and sinus beta. And we can use this formula here. we can use this formula here. According to this, we have that this is equal to xv multiplied by cosine omega 0 t plus alpha. Okay, do you have any questions about this? Do you have any questions about the solution of differential equation and about transformations of this solution? No questions. Okay, so I will clean some unnecessary information. So we have obtained the solution. We have obtained the solution in useful form. For practice, for calculations, and for describing oscillations. So this form is the most useful for us. So we will use this formula. So we have obtained a formula that describes so-called harmonic oscillations. What harmonic oscillations are? Harmonic oscillations are oscillations that can be described by cosine or sinus. So this is formula of harmonic oscillations, for harmonic oscillations. And let's try to draw a graph of this. It is quite simple to do. It is quite easy to do, to draw this graph. Graph of cosine is well known from math. If we have time, coordinate x. Now I will make two dash lines. I'll draw two dash lines. Now I will make it dash lines. I will make dash lines. Dash lines. Dash lines. So this is xv minus xv minus xv. Here we have 0. And the graph can be drawn in some way like this. graphs of cosine and sinus are very well known, so we have that here this is xv, this is xv, and what about this distance? I'll draw one more dash line. This is also dash line. And I'll find this distance. This distance is alpha divided by omega 0. This is alpha divided by omega 0. This distance is alpha divided by omega 0. So this is initial phase of oscillations. Initial phase, and xv is amplitude. Xv is amplitude. So from here we have that xv is amplitude. Is the amplitude, and alpha is initial phase. Is the initial phase. Okay, and if we have oscillations, we have periodic process. We know that cosine is a periodic function with period that is equal to multiplied by p. The period of cosine is equal to p. It means that we can find period of oscillations from here. Omega 0 t plus period of oscillations plus alpha. It is the same as changing the whole expression in parentheses, changing by 2p. So plus alpha plus 2p, because 2p is period of cosine. And from here we have omega 0 t plus omega 0 t is equal to omega 0 t plus 2p plus 2p. And from here we have that the period of undamped small free oscillations is equal to 2p divided by omega 0 divided by omega 0. So period of oscillations of period of oscillations period of oscillations period of oscillations t is equal to 2p divided by natural angular velocity or natural circular velocity. Natural circular velocity, and it also it can also be written as 1 divided by eta. Now I will explain this value. Eta is the number of oscillations per unit of time. Number of oscillations per unit of time, and this is called linear frequency. So where omega 0 is equal to 2p, where this value is linear frequency. So number of oscillations per unit of time. Maybe per second. Or minute or hour. But maybe let's leave this as written here, and omega 0 is natural angular frequency or natural circular frequency. circle of frequency. Okay, so do you have any questions? Do you have any questions? So we have just obtained the solution of differential equation of small free undamped oscillations. Small free undamped oscillations. Oh, no questions about this. No questions. Okay. Okay. If there is no questions, let's start learning damped oscillations. Damped oscillations. Damped oscillations means that there are energy leaks, energy dissipation in of oscillations. So there are some dissipative forces that try to prevent oscillations. So let's have a look at simple oscillator with damping. Simple oscillator with damping. I'll remind this that simple oscillator is a mass connected to the wall by spring, and here we have spring constant, and in case of damped oscillations, we have one more constant, mu, that connects velocity of body or material point and force that tries to prevent motion. Force that tries to prevent motion. So in this case, for simple oscillator, we have that force is equal to minus key x. This term we had from previous case that we have learned recently, that we learned on our previous lesson. But now we have one more term that is equal to mu multiplied by first derivative of coordinate. So mu is some coefficient of resistance, so some coefficient of resistance. This is some resistance coefficient, and it describes dissipation of energy in our system. Dissipation of energy in our system, and we also have that acceleration. Acceleration is derivative of velocity. Derivative of velocity, and it is also second derivative. It is also second derivative of coordinate. It is also second derivative of coordinate. So let's use second Newton's law of motion. Second Newton's law of motion. In this case, we have that this is equal. This will be m second derivative of coordinate by time, and this is the same as minus k x minus mu d x by dt and we can make some algebraic changes in this equation, and this can be written as d2x by dt 2 plus mu divided by m, dx divided by dt and plus k divided by mass m, k divided by m multiplied by x, and this is equal to 0. This is equal to 0. So we can write differential equation of free damped oscillations. It is differential equation of small free damped oscillations. This will be d2x divided by dt plus 2 beta dx by dt and plus omega 0 to the power of 2 x that is equal to 0. That is equal to 0. Okay, so here we used some new signations. So beta is equal to mu divided by 2m, and omega 0 is equal to square root of k spring constant divided by mass. A spring constant divided by mass. Okay, do you have any questions about this? No questions. No questions. Okay, if there's no questions, I will clean some information from the screen. I will clean some information from the screen. We have just learned a simple damped oscillator, but for other cases, the situation, the equation will be the same, and I will write the result, the final result. So simple oscillator. The first case is a simple oscillator. The second is torsional. The second is torsional pendulum. Torsional pendulum. And the third is physical pendulum. The third is physical pendulum, and the fifth and the fourth is mathematical or simple. Or simple pendulum. So for simple oscillator, we have obtained this formula. For torsional pendulum, in a similar way, we can obtain similar formula. Beta is equal to mu divided by 2 multiplied by moment of inertia, and omega 0 is equal, and omega 0 is equal to square root from d divided by I, where d is torsional constant, as you can remember from our previous lesson. So this is So for physical pendulum, we have beta is equal to beta is equal to mu is also equal to mu divided by 2I, and omega zero you can remember from our previous lesson. This is mgr divided by I, and the last case mathematical pendulum, beta is equal to mu divided by 2m, and omega zero natural angular frequency is equal to a square root from g divided by L. All formula for natural frequencies we obtained on our previous lesson. But beta we obtain only for simple oscillator, and for other cases we have written this without proof. And beta. So for all these cases, we have the same differential equation. And beta is damping constant or damping coefficient. Beta is damping coefficient. Beta is damping coefficient. Damping coefficient. So we have differential equations of small damped oscillations, of three small damped oscillations. And we have written this for different mechanical systems: simple oscillator, torsional pendulum, physical pendulum, mathematical pendulum, and for all these cases we have the same differential equation. It is necessary to say that sometimes you can see this in internet. You can see that beta divided by omega zero. Beta divided by omega zero, and it can be called damping coefficient. So sometimes you can see this. Sometimes you can see this in the internet or in some books of physics. Sometimes you can see this. So it is necessary not to confuse these values. Okay. Do you have any questions? Do you have any questions? No questions. No questions. Okay, so if there is no questions, let's try to let's start. Let's start. Let's start. Let's try to solve this equation. Let's try to solve this equation. First of all, we can make we can try to make substitution. We can try to make substitution in this equation. X is equal to gamma multiplied by y. So let's use this substitution. To do this, it is necessary to find first and second derivatives. First derivative, dx by dt is equal to gamma dy by dt by dt plus d gamma by dt y. This is first derivative. What about second? What about second derivative? What about second derivative? And second derivative is first derivative of first derivative. So it can be written as d by dt from dx by dt. Dx by dt. Okay, let's find this. Let's find this derivative. Let's find this. It will be equal to gamma multiplied by d2 y by dt to the power of 2 plus d gamma by dt dy by dt plus d gamma dt y. No, sorry, derivative dy by dt plus d2 gamma by dt2 y by dt2 y. So it means that we have that gamma multiplied by d2 y by dt2 plus plus 2d gamma by dt dy by dt and plus d2 gamma dt to y. Okay, so do you have any questions? Do you have any questions? Do you have any questions? No questions. Okay, so let's make substitution. Let's make substitution. So from here we have that this will be gamma d to y dt 2 plus 2 d gamma by dt dy by dt plus d2 gamma dt y. Okay, the second term plus 2 beta plus 2 beta 2 beta gamma dy by dt plus 2 beta d gamma dt y and plus omega 0 to the power of 2 gamma y is equal to 0. Okay, and let's divide left and right sides, left and right parts of this equation by gamma, divide by gamma, and make some algebraic actions. Make some algebraic actions for this case. So we can write that this is equal to d to y by dt 2 plus 2 1 divided by gamma d gamma by dt plus beta and this is dy by dt. dy by dt. By dt. So we have used all of this and plus open bracket d. No, it will be 1 divided by gamma. 1 divided by gamma. Or maybe it is better to write in this way. Omega 0 to the power of 2 plus 1 divided by gamma. 1 divided by gamma d2 gamma by d2 gamma by dt2 and plus 2 beta divided by gamma d gamma by dt y, and this is equal to 0. This is equal to 0. So we have made some changes. We have made some changes in our differential equation, and let's try to find such function gamma when this is equal to 0. Let's find such gamma when this is equal to 0. So to find this, we have to find partial solution of this differential equation. Plus beta is equal to 0. It must be equal to 0. It must be equal to 0. So this will be d gamma divided by gamma is equal to minus beta dt minus beta dt, and this can be integrated. D gamma divided by gamma and is equal to integral minus beta dt. And according to this, natural logarithm of the absolute value of gamma is equal to minus beta t. We have used that fact that beta is constant. Beta is constant, and according to this, the absolute value of this function gamma is equal to e to the power of minus beta t, or we can write that gamma may be equal plus or minus e to the power of minus beta t. We can use both. We can use both of these forms, and let's use form with plus. Let's use form with plus. So according to the written according to the written formula, we can write that this is so I will write that gamma is equal to e to the power of minus beta t multiplied by y. So let's use gamma is equal to e to the power of minus beta t. Okay, do you have any questions about this? No questions. No questions. Okay, if there is no questions, I will write the final result that we have obtained. So we have obtained that after this substitution, we have differential equations d2y divided by dt to the power of 2 plus omega 0 to the power of 2 plus 1 divided by gamma d 2 gamma by dt 2 plus 2 beta divided by gamma d gamma by dt y is equal to 0. So after this substitution, we have this differential equation. And I hope that we will continue to solve this next week. And tomorrow we are going to do exercises. We are going to do some exercises from oscillations and waves. Okay, do you have any questions? Do you have any questions? No questions. No questions. Okay, if there is no questions, so thank you for your attention. I hope to meet you tomorrow.
See you tomorrow, teacher. Have a nice day. Goodbye.
Have a good day, teacher. Goodbye.
Good, teacher.